Greetings and welcome to the RC Wall Vacuum channel. Today's video I'm going to be doing a little detour off the usual 5th scale big bore, and I'm going to jump into a driving accessory. This particular prototype I have here is designed more for 10th and 8th scale electric and nitros, just because of physics and weight. I may do a 5th scale version in the future, but 5th scale ain't all that great. They ain't really graceful flying. The stock and the small bores are. Big bore ain't all that graceful flying. Actually, I should say they're not that graceful in their landing. At least mine aren't. So let's take a look at this contraption. So I call this thing the random ramp, and as the video title implied, it is a computerized auto-adjusting RC ramp. The basic premise is as your vehicle is approaching from several feet out, a microwave frequency Doppler sensor will pick up the vehicle, and that will trigger a processor to produce a random number, and then that random number is converted to pulses sent to a stepper driver, and then the stepper actually runs the end kick plate up. You'll see that in a couple of minutes how that moves, and then it stays locked in that position until a vehicle travels across. And then that hit on the ramp is detected by an accelerometer, and then the accelerometer will trigger the processor to lower the kick plate back down at a slower rate. And I do that just so it doesn't overshoot the home switch. And then the home switch is over there on the side, and that's the Hall effect sensor. Once that's detected, that shuts everything back down and clears the FIFO buffer in the ADXL accelerometer, and then also enables the Doppler to reread. And I put the accelerometer in it just because the current microwave Doppler sensor I have in there is an omnidirectional, and it's pretty sensitive. I can lower the sensitivity by putting some resistors in the back of it, but I don't want to lower the sensitivity. I want to change the directivity of it to it. So after Christmas rush, I'm going to take and order some different sensors that are more directional. But even still, and the whole thing was, since it is so sensitive and omnidirectional, I didn't want a situation where that kick plate was just cycling back and forth because of false triggers. Originally I had planned on just using an accelerometer on this thing to pick up the hit on the ramp, and then have twin 5th scale servos spin the deck, but I just didn't think there was going to be an issue. I thought there'd be an issue with timing. I wouldn't be able to quite get that deck to move quick enough, and the other issue is the servos are $250 a piece, where my little homemade linear actuator back there was like $20 when I was able to make that for it. I'll go into that stuff more later on. So this thing, even though I got a laptop tied into it right now, it does not require the laptop in there. It's all a computer board is going to be built into it. And I designed this thing to work off of 4S LiPos. It actually consumes very little power. I'll go into more details about how some of this stuff works in the future, but my point is that the laptop does not have to go, neither does the DC lab supply. So in this video, I'm just going to go over and give some quick overviews of the technical details of it, and the build aspect of it, and then I'll give a bench demo, and then in a follow-up video I'll take it up, I'll get it packaged up better and take it up on the track and give some field tests. So stick around, I'll just give you a rundown of how this thing actually works. So as you can see, it's in a rather crude prototype stage here. I have to package up things better, solder up some boards, and initially for my test, since I don't have any 4S's here, I'm just going to put a 12-volt garden tractor battery in there. That will have low voltage detection in there for the LiPo, so you know, and with an RGB LED, it actually will be a red, green, yellow for voltage level, and it'll have an automatic shut-off on it. So I'll just give you a quick demo of what it's supposed to do. Right now it's been triggered, and it's actually moved to a random position. I got to do some work with a random number generator. I do have it being seeded from an analog input, which helps to make more random than just a straight processor generator one. But I got to change the range I'm looking for. So sometimes it short cycles because I don't have a low side on the random number generator. But anyhow, so I should be able to, actually it's waiting for a vehicle to come across, so I should be able to tap the ramp and to trigger the accelerometer. It should come back down and be ready for another Doppler set. So let's give that a test. Okay, there we go, it's coming down. I've run it down kind of slow just so I don't overshoot the Hall effect, which is located in behind this board. It's been working pretty good. I might switch to a lever mechanical switch, just a little more rugged. Now at this point, I should be able to wave out in front there, and it should pick into a random position. I have no idea where it's going to end up. So it went out pretty far this time. So now it's going to sit and wait for another trigger from the ramp, from the vehicle across the ramp. And there it goes. It's coming back down after that. I got to play around with the accelerometer settings too. I got a little too sensitive. I actually can, if I step hard on the floor, it'll be enough to trigger that thing. This thing's extremely sensitive. So I just got to play around with the math a little bit. I ain't got me no college education, so I gotta kind of fight my way through this stuff. So I'll start diving into some of the build details on this thing here. Let me get repositioned for that, and we'll go into that. So starting off with the mechanical stuff, it's made up of a mix of 6061 and 6063 aluminum welded up. It actually can all be disassembled and stacked away. It is, it's basically several sub-assemblies that can be unbolted. The deck here, I think that's like a 3003. Unfortunately, my brake wasn't wide enough to bend some of this stuff, so I wasn't able to put the bends where I wanted them. So this is the business end of it, and let's take a look at the back section of it. So I had started off with just a flat kick plate just to get it set up, and I was going to go to a curved one later on with a bent aluminum. Then I decided, no, I want to do something right from the start. So I just did a quick design and 3D printed these wedges to put in there and put this sheet metal on. And you can see where, since I don't have a bend brake, I got this sag in here, which I'll probably just do a couple short sections and wedge them in there, try to stiffen that up for now. Then over here we have the stepper, well, the linear actuator. I looked into commercial linear actuators and they were all pretty pricey, and the other issue is, like I stated, there's a timing. I need this thing to actually work fast, and most linear actuators are meant for precision, so they're usually fine thread. So between the cost of it and the fact that they're fine thread, and I wanted something with coarse thread, I ended up building this one myself. It's a NEMA 17 stepper, I believe, and I got some 8mm 1.25 coarse threaded heavy duty, I think it's like 125,000 PSI threaded rod. And this, I wanted low friction at the nut there. I machined that out of bronze. That's a nice slick setup there. And no, I did not steal the holder from the local airport bathroom, but it does look like I could have came out of something like that. Then I just got a U-joint down at the bottom of the shaft there into the motor to keep that from, so I can adjust any deviations as it goes through an arc. So starting with electronics, this is the Doppler sensor right here. This sits out in front of the unit. Eventually, I think I'm going to take and build a little pivoting trap door set up here where the sensor will sit right on top of there, and it might even have the accelerometer hooked to that. And then it'll be spring loaded on a pivot. As the vehicle comes up, it'll just knock that down out of the way and travel through. The whole point is so I can have it pointing right out to the front and be good contact and catch the vehicle from quite a ways back. But also, like I said, I got to switch to a more directional Doppler sensor. And I think that the ones I'm looking at are actually millimeter wave and not the microwave. So tucked up in there is the accelerometer. It's an analog device. It's ADXL345. Communicates on an I2C bus. And I do have the interrupt pin tied to the tap function, but I'm not currently using that. And so I just had, I got it mounted to the sheet metal where I figured it'd be the most vibration on there. I just whipped up a little carbon fiber 3D printed box to hold it for now. And but that's where the trigger gets fed from when the vehicle goes across the jump. So right here on this breadboard is the main functioning parts. I just got an Arduino R3 on there. This over here is a 5-volt buck converter. That's going to take the power from the LiPo. In this case, it's this lab supply, but it would normally take a power from the LiPo, drop it to 5 volts for the Arduino and the sensors and stuff like that. I need it to be at least 12 volts for the stepper. One of the issues with the timing of these steppers is you need the speed, and what's critical with the stepper motors is the winding inductance. So I got as low as the winding inductance as I could find, and it's pretty fast. I'm going to run it pretty quick on here. I might be able to play around with the software settings and bring it down a little bit more, but right now it's running pretty fast. Over here I got a level converter, and that changes the 5 volts down to 3.3 because the accelerometer is all 3.3 volt logic, and the I2C network is also 3.3. Then this up This right here is it's a DRV8825 stepper driver. I'm currently running that NEMA 17. It's good for a 2 amp, I believe, on the windings. I'm running it right now like 1.5 amps, or actually a little less. So I can go up in torque, but I don't see any point in, as long as it's functioning. I don't really plan on going up in torque. As far as power consumption goes, I just keep this thing. This DRV's got a really neat enable feature. The thing responds. I don't have a scope on it to see what the time is, but it's got to be in the picoseconds, maybe nanoseconds, but it's definitely in the picoseconds. Response between the time you turn it on and it's ready to go. So it allows me to basically activate the driver when I'm going to move it, and then immediately shut it off. And so the idle current on there is only maybe 20 milliamps with the whole thing sitting there. And then once you jump up to run the stepper, it goes, right now it's running, like I said, about 1.5 amps, I believe. But it's only on for a couple seconds, and then it's back down. So you should get a really good runtime out of a 4S LiPo on this thing. So I don't currently have the RGB and the low voltage detection in there yet. That'll be something I'll add later on when I put it to an actual board. But the rest of the stuff is there's on there, some support components, decoupling capacitors and things like that to quiet down noise. So that's the gist of the random ramp. Like I said, I'm going to take and package it up better, and I'll do some field testing yet. Should have some weather, decent enough weather yet this fall to give it some tests. I might even try something like run it in the snow, see how that works. But if you want to check it out, see the demos, check back in a little while and feel free to subscribe. I'd appreciate that. And but in the meantime, thanks for watching.